Yeah. Pretty exciting.
That's what I'm not sure.
I had some questions regarding the homework.
Yep.
I was working on the code over tonight. I don't know if I'm running into some issues.
Okay.
Yeah.
Is it errors in MATLAB or is it answers not matching up?
Errors in MATLAB.
Okay. Yeah. If you run into questions like that, you can email me. I try to answer as quickly as possible, but usually for code questions, it's easier if you kind of send me the code, and then I can kind of take a look and kind of debug it from there.
Well, I got it right here.
Okay. Let me get set up here and then we'll. Hey, Samson.
Plans for spring break?
More looking at houses and catching up with work and. My wife's been really busy, and so we haven't really had much of a break, and so yeah, we're just gonna stay in.
That'd be nice.
Yeah. How about you guys?
Senior design. Spring break's just senior design week for me.
I think that's how it is for everyone, unfortunately.
Might be going to Vegas. We haven't decided yet.
Okay. Nice.
We like have Jake's my fiance's aunt has like a timeshare out there or something. She's
Nice.
Like, do you want to take it for a week? I'm like, what's the catch? You have to have dinner with us. We're like, I don't know.
Oh man, those timeshares they get you.
I don't know.
My in-laws have them too, and so they
It's such a like Gen Xer thing.
It is.
So weird. Like, I don't understand, but you know.
Well, soon they will die because I think everyone in our generation knows that they're a scam.
Yeah, they're just called Airbnb now, right?
Yeah, that's true. They just call them a different name.
Yeah, we're still falling for it. Nice. Thanks. 7 years. Yeah, I think it's always nice to travel every now and then. You know, just get out and see the world. If you haven't traveled for so long, I think it'll be really fun. Where are you going, Samson? Nice. Oh yeah. You told me Hawaii. That'll be a lot of fun. A real getaway from everything.
4 years ago, I went to Japan during spring break. It was great.
Nice.
I went there just in time as the cherry blossom show.
Oh, nice. I've always wanted to go during that season.
Yeah. Spring break just happens to work for that.
Mhm.
So
Okay, let me go through the code.
we're talking about this code, but I'm not talking about like the things right now.
Yeah.
It's a really nothing.
I feel like I'm still missing that. But like I reviewed it a couple of times. I don't know more. What I might be missing.
Is that the only error? That's an error with video stuff, and so you guys shouldn't be getting errors with that.
This is what I get here, but I had this initially on my desktop.
So this is 3A.
Yeah.
Okay, let me look at. Okay, I see. Okay, so 3A is a explicit Euler. Now for explicit Euler, you're not doing any backslashing here. So for explicit Euler, what you should be doing is the matrix that you're building up. That's what you're multiplying by the current solution. So it should be, you might go for it. And so it should be after I've already touched it. And so it should be A multiplied by slope curve.
But the inverse of B.
No, without and so with explicit, there's no inversion going. And so this is what you should be doing. Because if you look at our like if you look at the structure, so this is for implicit, because implicit you have a lot of n plus ones, right?
Yeah.
But for explicit, remember, we only have one n plus one. That's on the left side. Everything else is n, so that's why it appears like that. So
Explicit. So this is implicit. So then my ends should be on the other side.
exactly, yes,
Okay,
yes. You might have to do it from the beginning because it changes up the signs for all the terms too. And the other thing that I see, so these coefficients here, the 1 minus 2, 1, this is works when it's a steady case. But for unsteady problems, we kind of move everything over to the coefficients. And so we should be like diffusion coefficient multiplied by dt divided by dx squared. So you should have a more complex expression. And so if you kind of look back at your notes, so look back at kind of the very first time we did explicit Euler. So if you have the lecture notes, I think it's note 08. 07, let's go to 07. Yeah, so this is the system that we just did. So this is the A times SOL curve plus B. That's basically what this is. So you have A multiplied by SOL curve. SOL curve is the phi I m plus B. And so that's what we're doing now. So you can scroll up a little bit more. Basically, you're doing this exercise right here, but for explicit. So I thought we did a general expression like this for explicit. I guess not. And so basically, a good exercise, and you can do this exercise too. If you look at the derivation we did here, we took the differential equation, and then we broke everything up to find differences, and then we got all these coefficients here, right? Do the same exercise, but instead of n plus 1, it'd be n, you're right. And then work it through with the symbols, and you'll get equations that look similar to this, but for the n variables. And then that's what you should put in your picture. You have the velocity, and so that velocity should be factored into the coefficients up top. That's how you have the time varying size. This coefficient or this velocity factors into the left-hand side.
Oh man, all right.
It's tough.
Yeah.
This the unsteady stuff is it's complicated expression.
Yeah, all right. I'll give it a shot. Thank you.
Yep.
Hey, how's it going? Good.
You do that on purpose. Just pure muscle.
Yeah, well, working on that example, I was looking at the codes, and there wasn't really much of an example code for 1D for me to like at least
I see.
get an idea.
I see. That's true. We never did one. We never did one that complex. So actually, there was. If you look at from lecture notes 8, if you look at our code for the vibrating string, actually no, we didn't really do that one in symbols either.
Yeah.
So yeah,
I was
that's
trying to
true.
look for that.
That's true. Okay, it's 3 o'clock. I mean, not 3 o'clock. It's 5:30. Man, I wish it was 3 o'clock. It's 5:30, so let's go ahead and get started today. So good evening, everyone. Today is our last lecture session before our spring break, and so that's exciting.
And so how's everyone doing today? Hanging in there? I know it's a stressful time, but it's you know, at least we'll have spring break. Let me go ahead and close the door. It's a bit noisy. Oh man, you just had work. Oh yeah, that'll definitely fry you. My mind's definitely fried after work every day too. Okay, so our plan for today is we're going to continue our lecture notes on the on diffusion modeling with finite volumes. Okay, but before that, I did want to talk about the final project. So probably what some of you noticed yesterday was I posted the specifications and the starter code for the final project, and so I did want to spend some time talking about that today. Just so that you kind of know what you're getting into and to give you some context. You know, technically, you know, by the end of homework 4, you should have everything that you need to do most of the final project. There is one small part of the final project that we'll get to later. But if you're going to do the project with finite differences, you have most of what you need already. So if you're interested, you can actually get started right now and then, you know, see how far you can get. So I didn't want to talk about that. And then after that, we'll continue on with our lecture notes. Okay. And so are there any questions about anything before we get started today? Okay, all right, so let me go ahead and share the screen. Oh, sorry about that. I had to close it because it was noisy. Thanks. Yeah, sorry about that. It was a little bit noisy out there, so I had to close the door. Okay, so let me go ahead and share the computer screen here. Okay, so we can talk about the final project. Okay. So I did a lot of thinking about the final project. Yeah, maybe just prop it open with the trash can. I think that's fine. Yeah, thanks for doing that. So I did a lot of thinking about the final project, and the topic that I settled on was cooling a hot room. And so I'm actually surprised that I haven't you know, use this as a final project yet because it seems so natural. But basically what you're going to do is you're going to be simulating, running a simulation of how a room is cooled on a hot summer day. Okay, and so to kind of motivate that, you know, I basically have this image here where, you know, temperature control inside of any building is always a very important aspect of engineering in general. Okay. And the tools that we're learning in this class can be used to simulate these kinds of situations, so you can better design them in practice. Okay. And so actually, let me start by showing you kind of the final result. You know, just so that you can kind of be aware of what you're going to be simulating. And so the final result looks something like this. There's no sound to it, so don't worry. Okay. And so this, so let me put this on repeat actually, so it's kind of going as I go. How do I repeat this? Whatever.
Back 3 dots. Back on the 3 dots. Repeat.
Repeat. There we go. Okay. So basically, what you're seeing here is that everything in yellow is a very, very hot temperature. Okay. And so what's going to happen throughout the simulation is that you're going to start by opening up a window here. Okay. And so that's what happens at the beginning. And so if you can see here, you know, it starts to kind of, you know, dimple a little bit right there. But just opening a window on this side is not going to be enough to cool the entire room. So what you're going to do after that is you're going to open up another window over here. Okay. And then that's going to help improve the cooling quite a bit, because what happens when you open this window is that a crosswind air is going to flow. Okay. And so that's going to modify the convection velocity that go through. And so basically you're going to have a flow of air that goes like this. Okay. And you can see that after this window opens, you know, it helps improve the cooling pretty significantly because you have a lot more blue here. And then it's a little bit hard to see, but at a certain point in the simulation, you'll start to see that the blue starts to swirl a little bit in this direction. Okay. I'll try to point it out when it first happens. So right here. So do you see that the room is starting to swirl a little bit? Okay. And so that's the effect of turning on a ceiling fan. And so if you've seen a ceiling fan before, you know, it spins at the ceiling, and the net effect of that is going to swirl the air. And so what that does is it helps spread some of the cooler air that's coming in from this window over to the rest of the room. Because before you turn on the fan, you know, even though it's cool if you stand next to the windows, you know, a lot of the room is still fairly warm. And so you need the fan to kind of make sure that the cool air kind of circulates all throughout. Okay.
So it's a fairly standard, I think what most people would do to cool down a hot room. I mean, besides turning on the air conditioning, and basically I'm going to have you guys simulate that for your final project. Okay. Okay, so let me go ahead and pause this for now, and let's go back to the project specs. Okay. And so, oh, question, yeah.
Was that kind of like a top view from the roof?
It is, yes. And so it's a top view. You're viewing the room from the top down. Yeah. Mhm. All right. So the formula that's going to be governing this situation is our normal kind of conservation equation. And so we have our unsteady term, we have our convection velocities and our convection terms, as well as our diffusion terms. Okay. So we have no source, and so we don't have anything that's producing heat in the room. But we are going to start with a fairly hot room, and then we're going to try to cool it as efficiently as possible. Okay. All right. And so if you, I don't know if you noticed, but in the video, the yellow indicated a temperature of 50 degrees Celsius, which is way too hot for any person to be in there. And so we have to cool this room as quickly as possible. Okay. All right. So here's your domain. And so you have a pretty standard square domain, the one that we've been working with this whole time. And we have a zero flux boundary condition at the outside, at least to begin. Okay? And so what's unique about this project compared to the codes you've worked on up to this point is that we're going to have different events kind of trigger at different times. Okay. I know we kind of just got done talking about how certain things like convection velocities and boundary conditions can change with time. Here we're going to have kind of discrete changes. And so we're going to have a part of the simulation where we have one window open. Okay. Then at another point in the simulation, a different condition is going to show up. Okay. And then at a certain point, the convection velocity is going to change into a swirling one. Okay. And so that's kind of the bigger step up for this project compared to what you've been doing for the homeworks. Okay. And what I've done here is that I've kind of broken up the problem into 3 parts. And so the first part of the problem, I want you to simulate just the opening of the first window. Okay. And so I've included these images to kind of help you benchmark your code. Okay. And so if you implement the first part of the code correctly, then your solution field should look something like this. And so you should have a little bit of a cooling here next to the window, and it's starting to spread out a little bit. Okay. After the second window is open, you should have a field that looks like this. Okay. And then after the fan is turned on, you should finally get a field that looks like that. Okay. And so I've included these benchmarks here just to kind of help you, because I think the thing when you're developing kind of a large code like this, it always helps to kind of do it in parts so that you can kind of make sure that one part is fully working before you move on to the next one. Okay. That's always kind of the best way to develop a big code like this, is to do it in chunks. And so this is kind of designed to help you so that you design just one part at a time. Okay. Okay. Any questions on this so far? Okay. All right. And so here are some of the requirements. Okay. And so what I've shown you so far is just the solution using the finite difference method, which is the only one that we've really talked about in detail. We're just starting to learn the finite volume method. Okay. But the finite volume method is also going to be possible for you as well. And so if you're more interested in doing the finite volume method, then that's going to be there for you. Okay. I don't have the starter code ready for finite volume yet, but I'll develop it, sometime after spring break. You'll have that available for you. Okay. And so if you're an undergraduate in the class, you can choose whichever one that you want. But if you're taking this class for graduate credit, you have to implement both methods. Okay. Since this is a 400 level class, grad students are required to do an extra assignment or extra work. And this is what the graduate assignment is going to be for this class. Okay. Okay. All right, so let's talk about some of the things that are new. So first thing that is new, actually, before the time gating stuff, is we're going to be working with the initial condition that's non-zero. Okay. Up to this point, we've just been working with a zero initial condition. Just like I mentioned, we have boundary conditions and convection velocities that change with time. Okay. And the other part that you don't have, that you're not equipped to solve just yet, is the fact that you're going to have some cross-stream diffusion that is occurring as well. Okay. And so the way that we're going to rectify this is through the implementation of a higher order scheme. And, because the video that I showed you there was for just a simple central difference for convection. But later on, we'll learn a better way to do convection, which will kind of get rid of this cross-stream diffusion. And so, we'll take care of it then. Okay.
All right, question. So would we have to use at least third order? Yes, and that's exactly what the higher order scheme means. And so for finite differences, we're going to learn a fourth order scheme later on in the class, and for finite volumes, we're going to learn a third order scheme that'll take care of that. But that's kind of way down the road in the class, and so you don't have to worry about that just yet. Okay, and so the time marching scheme that you're going to use is implicit Euler. And so in the past, I've kind of let you choose which one that you want, but implicit Euler is usually the best one for this. It kind of helps keep the solutions consistent as well. Okay. The number of time steps is going to be 400, and the time step size is going to be half a millisecond or 5 milliseconds. Excuse me. Okay. Okay. Any questions on the project so far? Okay. All right. And so there is quite a bit of code to write, although a lot of it you can take from the previous assignments. And so there's we've kind of written a lot of this code already, with some modifications. But I've kind of broken this down into a few steps to kind of help you kind of break it down for you. Okay. Step one is to just download the starter code. And so if you go to the final project page on Canvas, you should see a link for you to download a MATLAB script, which has a lot of the structure of the code there already. And so, of course, you're still going to be responsible for filling most of it in, but at least the starter code will give you, somewhere to start. Okay. All right. The second step is to implement the opening of the first window. And so here's kind of a schematic location where the first window is. Okay. The interesting part about this part is that there's going to be no convection during this part of the simulation. Okay. And so when you open the first window, heat is going to be released through that window, but it's going to happen only through pure diffusion. Okay. So I thought this was kind of a good first step because you have just pure kind of unsteady diffusion going on. Okay. And the boundary conditions will be given by the following. Okay. Okay. Another interesting thing is that the boundary condition that you're going to apply is not going to be constant all along the face as well. And so you're going to apply a different boundary condition for different locations, depending on where the window is. Okay. And so you're going to need to check what the y coordinate is along that face, and then apply the proper boundary condition, depending on that y condition. Okay. Okay. So I've left a lot of notes like this in the project specs, but I think what people tend to do in these projects is they try to kind of do everything at once. And so I really want you guys to do it kind of step by step. And so implement just the first step, get the Neumann boundary condition settled for this one. Make sure that your solution looks like this, before you move on to the next step. Okay. Because with the big code like this, I mentioned this before, the tendency is for things to kind of get lost. And so you kind of implement something and then you're not sure what effect that has, and you're kind of just shooting in the dark all the time. And so when you benchmark your code like this and kind of do it piece by piece, it really helps to organize your work, and it kind of leads to, I think, a much more efficient solution. All right, and so the next part after that is you're going to implement the opening of the second window. Okay, so you're going to have another window that opens over here. And so that's going to change the Neumann boundary condition there as well. Okay, so you're going to have a Neumann boundary condition where heat's going to flow out this window here. But the other thing that's going to happen is, because you have two windows open in the same room, okay, so you have a window open on the southeast side and also on the northwest side, it's going to cause air to flow from the second window to the first window. Okay. And so if you're familiar with the term cross flow, that's exactly kind of what we're seeing. And so if you've ever been in a hot room before and you open just one window, you don't really feel any air flowing through there, because there's nowhere for the air to go. And so it has to come into the room and go out from the same place. But when you open a second window, that allows air to clear path flow through the room. And so it allows the air to flow. In this case, it's going to flow through the second window and then out the first window. Okay. And so that's why people always say that, if you want to cool a room, or if you want to, air out a room, you need to open at least two windows so that the air has a clear path to go through. And then as the air flows through, it can take a lot of the heat or the smell or whatever along with it. Okay. So that's called cross flow. And so that's the simulation. That's the situation we're going to do in the second case. Okay. And so in addition to changing the Neumann boundary condition, you're also going to implement the following convection velocities. Okay. So you're going to have an x convection velocity of -1 and a y convection velocity of sine of pi x. All right. So that's part 3 of the code. Part four is when the fan is turned on. And so when the fan is turned on, it's going to change the convection velocities. And so it's no longer just going to be what's up there, but you're going to add these velocities to it as well. Okay. So I call these U swirl and V swirl. Okay. The important thing about step 4 is that you make sure that you don't overwrite the cross flow velocities. Okay. And so the swirling velocity should be added on top of what's there, but it shouldn't overwrite it. Okay, so make sure that you kind of do that for. Okay, and so those are the main three parts of the code. And so all of those you can implement already. Okay. Step 5 is to implement what's called the higher order scheme. And so we haven't learned this yet. And so you can't do this part of the project just yet. Okay. But you can do everything else and actually recreate the video that I've shown. And as soon as we've learned how to do higher order schemes, then you can implement this part as well. But that's about 80% of the work of the project already. Okay. Any questions on this? Okay. All right, and so the last thing is just to basically produce all the plots that you need for the final report. And so we'll go over the final report soon, and then just to write your report. And then I guess step 8 here is to profit, or at least enjoy your summer. Okay. Okay, so deliverables. And so deliverables, everyone's going to be submitting a final report. This is an individual project, so everyone's going to be writing their own code and writing their own report. Okay? And so I want you to do a lot of comparisons, basically. Okay? And so once you kind of finish writing the code, I want you to run it under a lot of different conditions. And so, for the first case, I want you to run the code with 3 different diffusion coefficients. And I want you to see how that affects your results. Okay. In section 2 right here, I want you to compare the results with 3 different mesh densities. And so I want you to run with a coarse mesh, 25 by 25, a medium mesh, which is 50 by 50, and a fine mesh, which is 75 by 75. Okay. Be careful of step number 2 here, because I think the temptation for a lot of people is to just run it with the fine mesh. Okay. I kid you not, with everything that's going on in this project, a simulation might take you 20 to 30 minutes to run if you have a fine mesh. Okay. And so I have a note here that said, before you run it with the fine mesh, make absolutely sure that everything else is working, because you don't want to be debugging on your fine mesh, because you don't want to have to wait 20 minutes for every simulation. Okay. And so make sure you run it, 50 by 50 should be okay for most computers, but you can even do 25 by 25, and that'll be even faster. Okay. Yeah.
We don't have to apply the diffusion changes onto those meshes as well.
No. So here I think I say, yeah. So for these ones, you're going to keep the medium coefficient here, and so you're going to have k is equal to 0.175. Yeah, you're only changing one thing at a time. Okay. All right, and so for the project, you don't have to go any finer than 75 by 75. You're welcome to try even more than that. I know the tempting thing is to try 100 by 100, but just be prepared to wait a long time for the solution. I was actually running it on my computer, 100 by 100, yesterday after I finished the specs, and it was running for about an hour, and it still wasn't finished. And so I kind of just gave up because it was kind of lagging the rest of my computer up. And so you're welcome to do that. I'm not going to give you an extra credit, but you're welcome to push your computer to the limit if you want to. Okay. Step 3 right here. So step 3 has to do with the higher order scheme. And so I want you to compare your results with the basic scheme versus the higher order scheme. Okay. And so all of that is standard. So everyone's going to be kind of doing, more or less producing the same plots for 1 through 3. Number 4 is where you can kind of demonstrate a little bit of creativity. And so in step 4 right here, I want you to play around with some of the parameters of the problem in order to improve the cooling of the room. And so think about, out of everything that you simulated here, the opening of the windows, the turning on the fan, the convection velocities, I want you to make a change to the code or change to the parameters to make the cooling a little bit more efficient than before. Okay. And so you can do almost anything to the code. And so I want you to describe what change you made, and I want you to explain why you did it. And I also want you to compare, how the results were before and after your change. Okay. All right, step 5, if you're taking this class for graduate credit, I want you to compare the results between finite difference and finite volumes. Okay, and so that'll be kind of just a way to kind of show that you did it. Okay, and then once you do all that, then that's everything that you need for the report. And so in addition to these plots, I still want you to submit your MATLAB code as well as a video. Okay, and so a video just to kind of show what the results look like. All right, and so after you run your code, I have this section here just to make sure that that you produce all the plots that you need, because that's going to be a big part of the final report. Okay, any questions on this? Yeah.
If you're doing the graduate level version, like, do you have to do all of the deliverables twice as well?
No,
Oh, okay.
no. So for all the other deliverables, you can choose one of your methods. So you can do finite difference or finite volume.
Okay.
The only one you have to show me both is just for step 5 right here.
Got it. Thank you.
Yeah. Mhm. Okay.
Quick question.
Yeah.
For the parameter change, you mentioned we can't change, what can't we change?
The only thing you can't change is the diffusion coefficient, because you already did that. And so because you already did that in step 1 right here, I want you to change something other than that. But you can change the velocities, you can change the boundary conditions, and so you can open up another window if you want. You can make the flow go faster. You can say that it's a windy day, right? You can make the fan go faster if you want. And so you can do any of that stuff. Yeah. Mhm. Okay, so let's talk about the final project or final report itself. Okay, so I have a structure that I want you to follow for the final report. I am going to post a template, and so you can use the template to kind of fill in your material. Okay. I don't have a page limit, and so I've however much space you need to communicate everything, that's how much space you need. And so I'm not going to ding you down or improve you based on the length. But everyone always asks me about how long do I expect the report to be. Based on what I've seen in the past, the reports are going to be around 10 to 12 pages on average. But again, yours might be longer, yours might be shorter. I don't grade based on the length. Okay. And so I'm more interested in it if all the content is there and all the questions are answered. So don't worry about the length, but if you want an estimate, it's about 10 to 12 pages. Okay. All right, and here are the sections that you need to include. Okay. Oh, the style. And so whenever you're producing any piece of writing, it's always important to know who your audience is. So that kind of dictates how you write and what level of detail that you use. And so I want you guys to write this report as if you're going to show this to one of your peers in your classes, right? So we do have quite a few of us here in this class, but there's also a lot of students that aren't taking this class. And so I want you guys to write the report as if you were going to explain everything that you're doing, in detail to that student, okay? And so what that means is that you can expect your audience to have some level of some knowledge of technical terms. And so, you don't have to dumb anything down. But they're not going to have taken this class. And so what I want you to do is I want you to write the report to, have your peer or have your friend kind of understand what you went through to produce these results. Okay. And so that's really important to know. Okay. And so first thing you have to do is you're going to write an introduction. And so that's pretty standard for these kinds of reports. Okay. Next, you're going to have a methodology section. And so this is an important part of the report as well. And so after the results, I think this is the most important section. Okay. And so I want you to describe a little bit of the theory that goes into your chosen method. Okay. So whether you chose finite difference or finite volume, I want you to describe it in detail. Okay. And so you don't have to do any full derivations. And so you don't have to do anything lengthy like we do in the lectures, but you should have, I think in the rubric, I say you should have at least 4 equations in your methodology section that really describe what you're doing. Okay. And so, remember, your audience hasn't taken this class yet, but if you explain it, with enough detail, with enough context, they should be able to have a rough idea of what you're doing. Okay. And so make sure you're defining all the specialized terms. So, don't just say finite difference, you have to define what that means to them. Don't just say implicit Euler, explicit Euler, don't just drop, a finite difference equation with phi ij's, things like that. And so make sure you define all your terms. Okay. Make sure you show your equations, okay, the main ones that you're using. And I want you to explain briefly about how those equations are implemented in the code as well. Right. So not just, the theory, but also a little bit of the implementation as well. Okay. And so, the kind of the tooltip that I have here is that kind of think of this as your opportunity to teach someone else about computational heat transfer. All right, so section 3 is going to be your results and discussion. And so, we just went over that. So that's all the plot that we talked about before. And section 4 is going to be your conclusion. Okay. And part of your grade is going to be on what I'd like to call aesthetics. And so that's kind of language, making sure that it's all clear and readable and understandable. Make sure the report itself, the figures are organized properly and it looks nice. And part of your grade is based on that. So, make sure that you proofread your report, make sure that all the figures are in the right locations and everything like that, because that's part of your grade. Okay. And that's part of the reason why I provided a template for you. So the template is there to kind of help you, organize everything into the proper sections. All right, so a few final things. This is an individual project, and so everyone's gonna be writing their own code. But with that said, it is a longer code, and so I do encourage you to work together with your classmates, especially if you're running into issues with with debugging. Okay. But the emphasis here is on working together. And so, I think what tends to happen sometimes is that, when you're working together on a coding project, one person or two people or three people will usually have pom-poms and they're kind of cheering on just the one person that's writing the code. And so I don't want that to happen. And so, ideally, if you're at a point where you kind of figured out the code, but someone else is asking you for help, help them through the thought process. Don't just give them your code and just copy and paste it. Help them through and help them kind of debug it on their own, because that's how they're going to get the most out of it. Okay. And part of the reason why I grade a lot on the methodology is because it's very clear when someone has just copied the code from someone else when they try to describe what they're trying to do, because they're not able to describe what they're going to do because they just copied their code. And so, if you do copy, it becomes very clear in the methodology. And so, just kind of keep that in mind. All right, so final remarks. I try to get this. I wanted to get this out to you guys before spring break, just so that you can start working on it, because it is quite a lot to code. It's a lot to do. It's a lot to write. But I'm as always with anything in this class, I'm here to support you. So if you're struggling with anything, please don't hesitate to reach out. And I'm always going to do my best to help you out. Okay. I always like final projects in classes like these because this class is unique, right? And so we don't really have another class like this in the college. And so a report like this can go a long way to helping you find a job or for grad school or anything like that. And so I like to have these final reports because you can attach them to your job applications. You can attach them to your grad school applications, because these are the things that really show that these are the things that really show what you actually learned in this class. And so most places will get your transcript, they'll know your GPA. That's fine, but a report like this is a lot more descriptive of what you learned in computational heat transfer, rather than just seeing that you got an A in the class or something like that. Okay? And so I like these final projects because it gives you something to show. It gives you something that you can remember the class by, and something that you can show off to people as well. All right, any final questions on this? All right, so that's your final project. And so I'll have the finite volume stuff. I'll have that ready probably sometime after spring break. But if you want to do with finite differences, the starter code is already there for you. Okay. All right, so let me go ahead and stop this. I'm gonna come back to the iPad. Okay. And let's go ahead and pick up where we left off. And so where we left off last Monday, 2 days ago, is we were talking about how to solve diffusion problems for diffusion modeling with finite volumes. Okay. So diffusion modeling with FVM. All right. And so at the end of lecture on Monday, we had just gotten our algebraic equation for diffusion modeling, right? And so remember the way that we obtain our algebraic equations for finite volumes is we take our governing equation and we integrate it over a cell. And then what we do from there is that we apply integration rules, right? So we apply divergence theorem and as well as trapezoidal rule to simplify the integrals, but also turn it into an algebraic expression. Okay? And just like we did with finite differences, we were starting with our 1D diffusion equation. Okay? And so remember, our 1D diffusion equation looked like this. So we had a minus k ddx of d phi dx. Okay, this is equal to q of x. Okay. And we had just gotten to the point where we obtained our algebraic equation. Okay, so we took this equation, we integrated it, we applied divergence theorem, trapezoidal rule. Okay, and we ended up with a very familiar frame. Okay? And so our expression here was PR minus 2 BC plus B sub L is equal to minus delta x squared divided by k times q of xc. Right, and so we have our very familiar 1 minus 2, 1, coefficients here. And this is for a case where we have an interior cell for our in our mesh. Okay? And so just to kind of remind you, we were looking at a situation like this where we have 3 cells in a row. Okay. C refers to the center cell. Okay. R, of course, I don't know my left from rights. R is the right cell, and L is the left cell. Okay. And remember, we're working under cell-centered finite volumes, and so the phis are going to be the neighboring cell-centered values. And so what we say is that when we apply this equation to cell C, okay, this is the equation that we get. Right? And so we need to find information from the left neighbor, from the right neighbor, okay? Just like we did with finite differences, except instead of neighboring nodes, we're looking at neighboring cells, okay? And this is equal to delta x squared divided by k times q xc. Okay. One kind of slight difference that you'll see, it doesn't make the biggest impact, but it does make a difference, is that when you evaluate the source terms, these are no longer evaluated at the nodes, right? So notice this is evaluated at x sub c, okay? Where x sub c here is the location of the self-centered. Okay. And so when we evaluate these source terms, they're going to be evaluated at the cell centers, okay? Not the edges. It's a subtle difference, but sometimes it can make a big impact on your solution. Okay. And so of course, the emphasis here is that, this works for an interior cell. But of course, now we have to work on what happens when we're out of boundary. And so this is kind of where the biggest difference between finite volumes and finite differences occurs. And so for finite differences, remember when we had a boundary condition, the boundary condition itself became its own equation. Okay. For finite volumes, that's not going to be the case. And so in finite volumes, our boundary conditions are instead going to modify our equation above. Okay. And so for any cells that border the boundary, their equations are still going to be, you're still going to get a finite volume equation from them, but they're just going to be a little bit different than the other ones because the boundary conditions are going to affect it. Okay. And so some people don't like this fact because, for up to this point, when we look at a boundary condition, we just said it's kind of its own thing, and and we don't have to, think about it too much. Okay. Here, you kind of have to worry about, how is this not that this boundary condition is going to produce its own equation, but how is it going to affect the equation that we have above? Okay. And so let me kind of give you an example. Okay, so let me see 2, 3, 4. Okay. And so in this situation, we have 4 cells, right? So we have cell 1, cell 2, cell 3, and cell 4, right? So fairly coarse mesh, but I think it's the best that I can draw on short notice. And so cells 2 and 3 are completely interior, right? And so we don't have to worry about cells 2 and 3 because we can just use the equation that we have above right here. Okay. For cells 1 and 4, cell 1 obviously borders the second boundary. Cell 4 here borders the right boundary. Okay. These are still going to have finite volume equations. But they're just going to be modified compared to the version above. And that's what we're going to talk about next, but how we actually modify these equations in order to take the boundary conditions into account. All right. Any questions on any of this? Okay. All right. So let's go ahead and talk about how do we do boundary conditions in finite volumes. Okay. And so we have two different types of boundary conditions here. So we still have Dirichlet, we still have Neumann boundary conditions. Okay. And so let's go over each of them. Okay. And so let's kind of recall our definition for the Dirichlet boundary condition. So for a Dirichlet boundary condition, these specify the value of the solution at the boundary. And so let me draw kind of a shortened version of this. Okay. And so let's say that our Dirichlet boundary is here, okay, on the left-hand side. And so this node right here will have a specified value of phi naught. Okay. So this is our Dirichlet value. The cell that we want to find the equation for is the one that borders that. And so here we have, this will be our phi sub c. Okay. And since we don't have a right, and since we don't have a left neighbor, the only one neighbor we have is a right, this will be phi sub r. Okay. Okay. And let me do this too. And so, just to kind of emphasize that, let's cover this equation with square brackets. The right boundary of the cell that we're interested in is going to be at location x sub r. And the left boundary will be at location x sub l. Okay. All right, so let's form the finite volume equation for this, and let's form it at the point right before we plugged in the kind of the slope values. Okay. And so let's form it for cell C. And so this is basically right after we performed our divergence theorem on this equation. Okay. And so right after we perform our divergence theorem, this is the equation that we get. And so we have the value of the derivative of our solution at the right boundary minus the value of the derivative at the left edge of our cell. Okay, all is equal to q xc times delta x. Okay. Okay, so let's plug in expressions for these derivatives. Okay. So let's start with the right side. And so the right side is fairly straightforward. Okay. And so just like we did before, we're going to assume a linear variation between between the cell center values, phi sub c and phi sub r. So phi r minus phi sub c divided by delta x. Okay. And again, this assumes linear variation between phi sub r and phi sub c. Okay. Right. So remember, delta x here is the distance between the cell centers. It could also be interpreted as the size of the cell. Okay. And so if we assume that the variation is linear between phi sub r and phi sub c, then the slope of that line is going to be phi sub r minus phi sub c. Okay. That was what we kind of went over at the end of class on. Okay. We can do the same thing on the other side, right? And so we can assume that we have a linear variation. And so if we have a linear variation between phi sub c and phi sub o, okay. Right, we can do the same thing there, except we can't plug in just delta x on the bottom, right? Because the distance between phi sub c and phi sub o is not delta x, but it's delta x over 2, right? And because it's only half the distance, because we're only traveling a half cell length in between phi sub c and phi sub o, okay? Right, and then the right-hand side is still going to stay the same. So we have q at x sub c times delta x. All right. And so all we've done is we've just kind of plugged in for those variables there. Okay. And so again, after we apply the divergence theorem, we have these expressions here for the derivative of the solution at the cell edges. Okay. And all we did was just plug in a linear approximation of what that slope is. Okay. So this right here is a slope, and this right here is a slope. Okay. All right, and so that's how we got those equations right there. Okay. All right, any questions on any of this? Okay, all right, so let's go ahead and evaluate this. Oh, question, go ahead. Yeah, so the question is why divide by 2? And so we divide by 2 on the other side because this is a difference between phi sub c and phi sub o, okay? Let's look at the difference between phi sub c and phi sub r, right? And so let me go ahead and draw the image again. And so, we have, this is the separation. Let's just assume that phi sub c is down here and phi sub r is up here. Okay? And I'm going to draw a line in between them. Right? And so what we want to approximate is d phi dx, at x sub r. And so we want to find the slope of the solution line here. Right? And so the way that we compute this is simply just rise over run. And so we take the rise as phi sub r minus phi sub c, and we divide it by its distance, its horizontal distance. Okay, so this is delta x, and that's how we get the slope. For the Dirichlet boundary condition, we only travel half that distance. And so here we have phi sub o, and then we have phi sub c. Okay. Again, we can draw a line. Okay. And so we're going to apply the slope right here. And so the slope here is phi sub c minus phi sub o. Okay. But the distance in between these 2 points is only delta x divided by 2. It's not a full delta x, right? Because the phi sub c here, or phi sub o, excuse me, the phi sub o is located right at the boundary because that's our Dirichlet value. Okay, so it's not a full cell over, but it's actually at the edge of that cell. And so that distance between phi sub c, phi sub o is only delta x divided by 2. Right, so that's why we have delta x divided by 2 on that edge. Okay. Is that does that answer your question? Great, awesome. Okay. All right, so now the next step is just to work out the mathematics for this. And so I'm going to go ahead and divide both sides by minus k. Okay. And I'm going to multiply both sides by delta x as well. Okay. And so if we do that, we end up with the following. And so we have a phi sub r minus phi sub c. Okay. Then we have a minus 2 phi sub c, okay, plus 2 phi o, okay. This is equal to minus delta x squared divided by k times q at xc, okay. We can combine these two. And so if we combine these two, we have phi sub r minus 3 phi sub c. Here we can make one more change actually too, because remember the phi sub 0, this was our Dirichlet value. And so this was known. And so we already know what this Dirichlet value is. And so we can take this as a known quantity and shift it over to the other side of the equation. And so what we have here is a minus delta x squared divided by k q at xc minus 2 phi naught. Okay. And so this is the algebraic equation that we would get for the cell that borders a Dirichlet boundary. Okay. All right. And so I want you to be careful here, because I think the temptation is that, when you have an equation like this and you see a Dirichlet boundary, you just kind of plug into this expression right here. Okay. This example that we did assumed that our Dirichlet boundary was on the left side of our cell, right? What happens when our Dirichlet boundary is on the right? Okay. And so if we were to look at a cell, okay. So let's say this is phi sub c right here, but the Dirichlet boundary condition was on the right. The question is, are you going to get the same equation right here? Okay. And so if you work on finite volume methods enough, the answer to this is fairly obvious. But for you guys, just because you guys are just learning this for the first time, I want you to kind of work this out. And so if you do come across a homework problem where your Dirichlet boundary is on the right, then I want you to go through the exercise that we just went through. And so start with the finite volume equation, plug in the approximations for the derivatives there for the slopes, and then actually get your algebraic equation here. Okay. And so what can change is that this coefficient might change right here, right? The coefficient that you have in front of the phi sub c term, okay, as well as the sign of what you have on the right, okay. And so it might not be a minus, and so I want you to kind of work that out. In 1D is going to be fairly obvious what's going to happen, but the reason I'm saying this is that when you go to 2D, in 2D things get a little bit more hairy, and so there's kind of a lot more stuff going on. And so if you start to take kind of shortcuts on the signs and on the coefficients, then that's kind of where mistakes are made. And so kind of, for the first few times that you do these, I want you to actually work them out by hand, right? And then based on those, then you start to build intuitions. Because in the past, and if you read the lecture notes, I have the answer to this question already in the lecture notes. But I think I've seen people kind of get stuck in taking some shortcuts with this. And so I want you to kind of work these out just the first few times that you do it, just so that you can kind of answer these questions. And then once you've done it a few times, then it becomes pretty obvious about what you should do in these situations. Okay. But the signs and the coefficients, people can get caught doing some shortcuts. And so I want to make sure that you do them at least the first few times, and then after that, then you can start to take those shortcuts. Okay. All right, any questions on Dirichlet boundary conditions? Okay. All right, so that's Dirichlet. Now let's look at Neumann boundary conditions. Okay. So let me go ahead and define Neumann boundary condition again. And so for finite volumes, actually, we're going to have a slightly different definition for Neumann boundary compared to before. And so it's not really going to make a big impact until we get to convection. But this change of definition is designed to kind of help us simplify our mathematics. And so the way we're going to define our Neumann boundary condition is that we're going to say that it defines flux, the solution flux at the cell boundary. And that'll be clear kind of once we kind of work it out. Okay. And so to illustrate this, I'm going to do an example where we have a Neumann boundary condition on the right side. And so we have our cells like this. And so let's say that our flux on this side is known. Okay. And so the flux that we have is this gamma variable here. All right. And so for this, we have a center cell, phi sub c, okay? And we have a left neighbor cell, phi sub L, okay? And we want to find out what the equation is for phi sub c that incorporates this Neumann boundary. Okay, and so just like we did with the Dirichlet boundary condition, we're going to start with our finite volume equation. And so our finite volume equation is minus k dphi dx. Okay. And this is going to be on the right side of the cell minus dphi dx at the left side of the cell. Okay. This is equal to q at xc delta x. Okay. And so first thing we're going to do is we're going to approximate this this slope. Okay. And so for this slope, we're going to take phi sub c minus phi sub L, and we're going to divide that by delta x, which is the space in between them. Okay. All right. And so that's going to be equal to q at xc times delta x. Okay. And we have minus k out in front. We have minus sign there. All right. And so at this point, we have to plug in an expression for d phi dx at x is equal to r. Okay. And xr, remember, is this side of the cell. And so it's going to be on this side right here. Okay. Okay. And so I know I've been calling this the solution slope at the different edges of the cell, but the other interpretation of this is this is the flux of the solution due to diffusion across the right side of the cell. Okay, so this is also the diffusive flux. Okay, the diffusive flux outside the right side. And so if that's the flux, then let's just go ahead and plug that in, because the flux on the right side is being defined exactly as gamma, which is our boundary condition. So let's plug in gamma right here. Okay. And that's going to be our, that's it. Okay. And so the nice thing about finite volumes is that it actually makes Neumann boundary conditions a little bit easier, because you can just kind of plop them right into the equation. Okay. And so let's go ahead and simplify this just like we did before. Right, so just like we did before, all of the known quantities. And so gamma here being a known quantity, we're going to move that over to the other side of the equation. Okay. And so if we do that, and we kind of work everything out before, we get a minus phi sub c plus phi sub L is equal to minus delta x squared divided by k q at xc minus delta x gamma. Okay. Okay. And so this is the equation that you get for a Neumann boundary condition on the right. Okay. Phi sub, oh, sorry about that. Yeah, my writing is terrible as usual. And so phi sub c is the one with the minus sign, And then phi sub L is that one. Yeah. Okay. Any questions on this before we do another example that kind of puts all this together? Okay. All right. So let's do an example here. Oh, actually, this example will give you the answer to the question I gave you before. Okay. So let's consider the following equation. And so we have 3d squared phi dx squared is equal to 2x squared. Okay. So that's our equation. And our boundary conditions are, we have d phi dx at x is equal to 0. So this is on the left side of the domain. So this is going to be 0. And so we have a 0 flux boundary condition on the left. Okay. And on the right, what we have is we have a Dirichlet boundary condition. So on the right, we have phi at 1 is equal to 10. Okay. And of course, our domain here is 0 is less than or equal to x, which is less than or equal to 1. All right. And so we want to find the finite volume solution. Okay. For n is equal to 4 cells. Okay. So our domain is going to look like this. Okay. So we have cell 1, cell 2, cell 3, cell 4. Okay. And so here we have d phi dx is equal to 0, and here we have phi is equal to 10. Okay. And so these are kind of the opposite conditions that we just did, and so you'll get the answer to these questions kind of very quickly. Okay. Any questions on this? Okay. All right. So let's go ahead and apply these equations. And so first thing we're going to do is, because they are interior cells, they're a little bit easier to work with. Let's write out the equations for cell 2 and 3. Okay. And for cell 2, what we have is phi left, and so the left neighbor for 2 is phi 1 minus 2 phi 2 plus phi 3 is equal to minus delta x squared divided by 3, okay? Because k is equal to 3 in this problem. And our q here is 2x squared, and so we have 2x2 squared. Okay. And then we have a similar equation for cell 3. For cell 3, we have phi 2 minus 2 phi 3 plus phi 4 is equal to minus delta x squared divided by 3 times 2x3 squared. Okay. And I forgot to mention, so x, when I say x1, x2, x3 here, they refer to the locations at the centers of the cell. So this is x1, this is x2, this is x3, this is x4. Okay. Because remember, when we evaluate our source function for finite volumes, we're evaluating them at the centers of the cell. All right. Any questions on this so far? Okay. All right. So let's go ahead and work on the boundary cell. So let's go on cell 1 first. Okay. And so in cell 1, just like we did before, I'm going to write out its finite volume equation. And so we're going to have d phi dx. Okay. And this can be evaluated at x r minus d phi dx evaluated at x l, okay, is equal to We know what Q is here, and so we're going to say this is equal to 2x1 squared. Okay. All right. And so let's go ahead and fill these in. And so for d phi dx at xr, this is going to be equal to phi2 minus phi1 divided by delta x. Okay. And then on the left-hand side, we have a predefined flux, right? And so the flux here is 0 in this case, since we have minus 0. Okay. So this is our Neumann flux. And so this is equal to 2x1 squared. Okay. Well, I guess we can plug in for k as well. So k here is going to be 3. 2x1 delta x. So there's a delta x here as well. Sorry about that. Okay, and so from here we can just simplify. And so if we just multiply both sides by delta x, we divide by -3, we have phi2 minus phi1 is equal to minus 2/3 delta x squared. Okay. And that is our equation. And so now that we have an equation for the Neumann boundary condition on the left, compare that to the equation above where we had a Neumann boundary condition on the right. Okay. And what you'll see is that they're basically the same. And so we have a coefficient of -1 on the cell that actually borders the boundary. And so in this case, the cell that borders the boundary is phi1, and then its neighbor cell has a coefficient of +1. Okay. Right, and so finally we have our boundary cell 4. Okay. Okay, and so just like for that one, we're going to form our finite difference equation. And so we have a minus k d phi dx at xr minus d phi dx at x sub l. Okay. This is equal to q at xc delta x. Okay. All right. But the difference now is that we have a Dirichlet boundary condition on the right. And so we have I'm going to go ahead and plug in for k. And so I'm going to plug in 3 for k. And so we have -3 times b naught minus phi4. Okay. All divided by delta x divided by 2. Okay. Minus phi4 minus phi3 divided by delta x. Okay. Right, so this is equal to 2x4 squared delta x. Oh, I forgot an x1 up here. X1 squared. Right, and so we know x0 here. So x0 we know is 10 because that's the Dirichlet boundary condition on the right. Okay. And so we plugged in 10 for that. And then we're going to do the same thing as we did before. So we're going to work through the algebra here. And so we're going to have we're divided by -3 on both sides. Okay. And so on the left side here, we have a 20 because we have 10 divided by 1/2, which is 20. Okay. Minus a 2 phi4 minus phi4 plus phi3. Okay. This is equal to minus 2/3 x4 squared delta x squared. Okay. And so we can move this 20 to the other side, because it's a known quantity. And what we get is a -3 phi4 plus phi3 is equal to minus 2/3 x4 squared delta x squared minus 20. Okay. Okay. All right, and so there's our 4 equations. And so we have, the first 2 equations that came from the interior cells, and we have these 2 equations that come from the boundary cells. Okay. All right, and so next I'm going to put it in matrix form just so you kind of see it all together. And then I was going to go over the code for this, but I think we're just about out of time. I do want to spend a bit more time talking about the codes because I think that seems to be kind of a pain point for kind of everyone in the class. And so I don't want to kind of rush through the codes like I've done before. And so we'll save the codes for after. We'll save the code for after spring break, and we'll go over it a lot more carefully. Okay. But before we leave today, I do want to put this in matrix form so you can see it all together. Okay. So any questions on this before we show the matrix form?
Yeah, how come before you would say that each cell would have a boundary on the left and right?
Yeah.
But then now we only do on the cells themselves.
Yeah, so I kind of regret, I'm using boundaries to kind of refer to 2 different things. And so I'm trying to be a bit more careful. So for the cells, right, each cell has kind of a left and a right edge to the cell. And so when I say that we're evaluating the slope here on the left edge and the right edge, that's kind of what I'm referring to there. When I'm talking about the boundaries, I'm talking about the boundaries for kind of the entire domain itself. And so that's why cells 1 and cell 4, we call those the boundary cells because they border one of the global boundaries of the entire domain. And so one of the edges so for cell 1 right here, so the left edge of the cell 1 borders the actual boundary of the entire domain. And similarly for cell 4, the right edge of cell 4 borders the boundary of the entire domain. Yeah. Mm-hmm. Yes, I'll try to be a bit more careful, talk about edges and boundaries, because I know it can be a bit confusing. Okay, so let's go ahead and put this in matrix form, and then we'll wrap it up for spring break. Okay, so first we have the equation for cell 1, and so let's go ahead and see up here. And so for the equation for cell 1, we have a -1 on the diagonal. Okay, we have a coefficient of 1 for phi2, okay, and no entries for the other ones. So this is phi1, phi2, phi3, phi4. Okay. Next, we have the interior cells, and for the interior cells, we have -1, 2, 1, 0, 0. Or excuse me, I screwed up those negatives. So there should be a 1, -2, 1. Okay, 1, -2, 1, and then 0. And then finally, we have this last equation here. So we have 0, 0, 1, -3. Okay. And then on the right-hand sides here, we have all of the right-hand side forcing vectors. And so we have, let's see, delta x squared divided by 3 times 2x1 squared, delta x squared divided by 3, 2x2 squared, delta x squared divided by 3, 2x3 squared, delta x squared divided by 3, 2x4 squared. And then this last one here has a -20 that comes from the Dirichlet boundary conditions. Okay. And so there's our linear system. And so just like finite differences, we end up with a system of equations. And then once we have these system of equations, we can invert them to solve for the phi values. Okay. Any final questions on this before we wrap it up for spring break? Okay. All right. So have a great spring break, everyone. I am working on your next homework, but I don't want to assign it until after the spring break. And so I want you guys to kind of rest from at least from this class a little bit. I know I gave the final project, but you don't have to work on it. It's not going to be due. Oh, I never talked about the due date for the final project. And so the due date for the final project is May 23rd at 11:59 p.m.
Graduation day. Yeah, or walking.
You guys can be on your phones and submitting your codes while you're waiting to go graduate. It's due that day, but you don't have to turn it in that day. You can turn it in before, but you know, I wanted to push it back as far as I can because the grades are due at the end of that week. And so that's kind of as far back as I can push it. And so, you know, and so I didn't want to have it due before finals week. And so this is when it's going to be due. So it's going to be due after finals. But I guess you guys are going to be graduating that day. So so maybe try to finish it before. Yeah. All right, question. So how many more homeworks do we have? I think we have 2 more homeworks. And so we have the homework 4 that's due this Friday. There's a homework 5 that I'm going to assign right after spring break. And then there's going to be a homework 6 right after that. So there's 2 more homeworks after this. Yeah. Okay. All right. So that's it for me. So thank you guys for coming. I know the class before spring break is always the hardest to come to. So I appreciate you guys coming out here. Have a great spring break. You know, I know you guys are gonna be working on senior design stuff, but you know, try to at least to take a little bit of a break. You know, your guys' minds deserve it, okay? Because you guys are working really, really hard. So thank you guys for coming, and I'll see you guys. I'll see you guys after spring break. No break until graduation. That's fair. That is fair.
That's
So at least you'll have a break from this class. Yep.
Is there a reason you dropped the negative out of all like the sociologies?
Uh,
Or is that not?
it is because I am being sloppy. So yeah, there should be a negative.
All right, cool.
Yes.
Thank you.
Yeah. Thanks for catching that.
Yeah. I thought it was like I don't know. I forgot how to do it. It's been a while.
Thanks, you too. Yeah, my brain is a little bit fried right now too.
You can't make us do that.
Thanks, Eddie. You too. Have a good break. Thanks, Kevin. Oh, if you haven't picked up your exam yet, I have it here if you want. Or you guys forget. You guys are good.
Are you going to office hours tomorrow?
Oh, what?
Are you going to go to office hours tomorrow?
Oh, yeah, for sure.
Okay. I got stuff on the 442 homework. I feel like it's not that hard.
Oh.
I can't figure it out.
It's yeah, if you haven't used the MATLAB stuff before, it is a little bit weird.
Yeah, it's like that's the problem. One of the second coding problem. Like I can't figure out how many lines of code I need or something. I don't know.
Okay.
I just
Yeah, if you're free tomorrow, just come on by. But if you're not free, just send me an email and then I can help you out.
okay, cool. Thank you.
Yeah.